So now I want to talk about, so we went through our basic idea. We saw that we could calculate, or with that, the idea behind uh, the idea behind calculating volumes with integrals relies on, in some way, constructing some area function along some interval, and then integrating that area function along that interval to to calculate the volume of that, like, three-dimensional object. Okay. Now, in our case, we were talking in full, like in just abstract generalities. But now we're gonna put a little flesh to it by talking about two of the different main ideas that we're gonna use to do these kind of problems. Okay. And so to do that, what I'm gonna do is I'm gonna derive these formulas for you. Okay. So the first kind of volume that we're gonna talk about is the volume of revolution. Okay. So let's imagine that this is my x-axis, and again, it doesn't have to be the x-axis, but let's say it is for our discussion. Let's say this is the y-axis. Okay, and let's say this is some value a, and let's say this is some value b, and for the purposes of our discussion, let us have, like, this be my f of x. Okay, in other words, f of x is a function which in this interval is only positive, and let's say what we want to do, or the way that this shape is formed, is as the revolution of this shape about the x-axis. Okay, so down here, let me see. Oh my God! I think after this act of drawing, Michelangelo would even stamp me as a master draftsman. No, I'm just kidding. But you can see what's happening. What's going to happen here is that I want to calculate the volume of this figure that's obtained by rotating it about the x-axis like this. Let me very delicately see if I can draw, like, what a cross-section looks like here. Right? You get the picture, right? But look at what's important. So now here, look at this. Let's say this is at that value x star, right? That we were talking about in general. I want to find out what the area of this slice is. Okay. Well, since I rotated this about the x-axis, it will be a circle, right? We remember that in general, the area of a circle of radius r, okay, is equal to pi r squared, right? And of course, I know I don't have to draw the figure for you, but just for fun, I want to draw the figure for you so you can see it. I want the area of this circle with radius r. The formula is pi r squared. Look at this. Look at this. This rotated, this circular slice at this value x star is a circle, right? What's its radius? It's going to be f of x star. It's going to be f evaluated at that particular x value. So what's the area of that circle, of this slice? The area of this circle will be pi times r squared. In this case, f evaluated at x star squared. Aha! So now we remember our volume formula. Our volume formula, when we were speaking in generalities, was the integral from a to b, where a to b either represent the extremities of the extent of the three-dimensional object in totality, like the extremities of the whole object, or at least the extremities that are of interest to the piece of the object whose volume we want to calculate. Let's say we only wanted to calculate from here to here, the volume of this object from here to here. Then we would then whatever x value this would be the new a, and this would be the b, right? And I know you get the picture. So this is the integral of a to b of a of x dx, right? This was in general. In this case, the volume of this revolution is going to be equal to the integral from a to b of pi times f of x squared. Okay. Okay. So this is going to be, this is known also as the disk method. Okay. But what I wanted you to see here was that it was a natural extension of our previous discussion. Basically, in our general discussion that came before this one, we were looking at some figure. We realized that if we could slice it like a loaf of bread, then each slice would have some area on the face, on the cross-sectional face, and that we could multiply that area by the thickness of the slice, and that would give an estimate of that piece of the solid. And so then when we added up all the volumes of the pieces, we would get an estimate to the volume of the whole thing, right? And then when we took the limit, as we sliced it into smaller and smaller slices, we could get an approximation to the area, to the volume of the figure that is better and better, okay? And so, and that gave us this formula. But then we saw here that in the particular case of a function, let's say f of x, that we're going to rotate about the x-axis, then that makes the cross-sectional area very easy to evaluate by using formulas that we know from geometry. And that gave us this volume formula. Okay? Okay. So this is the disk method. By the way, we're going to do an example of this in a few moments. Okay?